No. Sorry? It's about 60 to 80 degrees. That's what we get with a wide field lens. So just your monocular vision is quite thorough. Right? Now, of course, you combine it with binocular vision, you get 200 degrees field of view, right, in width, about 135 in height. Okay? Now, remember, this is just field of view. This is not this full space where you perceive depth. Okay? Where you actually see stereo vision is going to be about 120 degrees by 135 degrees. That's the range where images will overlap for the two eyes. Okay? So our depth perception ability is limited to about 120 degrees, 135 degrees in height. Okay? All right, what else? Some basic things. Your retinal area generally is about 5 centimeter by 5 centimeter. The thickness of your retina is about 0.4 millimeters, fairly thin. 1 degree of visual field on your retina is going to be about 0.3 millimeters. You normally stretch your hand out and put your finger up. That's generally about 1 degree visual field. The finger is going to project onto about 0.3 millimeters of your retina. You have about 5 million cones in each of your retina, 100 million rods in each retina. Okay. Peripheral vision is very, very important for us. Okay. We may not see details around the periphery, but it's very important because obviously it's a defense mechanism. Things that you cannot see in detail, you want the smallest change in contrast to be picked up. Low light changes. Right? That's what rods are great at. So you have lots and lots of rods all over the retina except for the fovea. Right? So you have 100 million rods. The diameter of the fovea is about 5.2 degrees, 1.5 millimeter. Right? So this is where you see your best. About 5.2 degrees, that's it. Okay. Now the minimum number of absorptions for any kind of detection, for any photoreceptor to actually sense something, for rods it's just 1. Right? Low light detection, scotopic detection is 1. Okay. Sorry, for rods normally it's just 1. A single photon of light coming through will fire it off. For scotopic detection, in order to actually differentiate something, it needs about 1 to 5 photons coming through at night time. And of course, for photopic detection, you need 10 to 15. Right? Much higher number of photons need to come through during daytime. Okay, so any questions on the human vision system? Everything good? Okay. All right, so let's translate the basic optics that we looked at into a very simple projection model so we can start creating relationships between what we see in 3D space to what gets projected onto our retina or, for that matter, any other sensor that we can talk about, right? So the process of projection is relatively simple. What you have is an object that exists in 3D space, right? It's going to get illuminated by some kind of a light source, and it's going to reflect a portion of that light. The reflected light is going to pass through some kind of a lens system, and it's going to project back onto a sensing surface, right? Whether this be a retina or any other kind of sensing surface. Now, of course, if you look at the basic geometry of rays, it turns out that a projection system like this will always generate an inverted image. Right? So, by the way, does this hold true for the retina? You think the projection is inverted for the retina or not? Yes? Right? Yes, it is. It is. So, the same ray system works for the human vision system as well. Now, of course, the distance between the sensing surface and the lens is typically referred to as the focal length. Right? This distance is usually fixed. Okay? Now, the simple projection geometry results in what we call perspective projection. Okay? Perspective projection is nothing but a reduction in dimensionality. Okay? When you're working in 3D space, we have 3 dimensions, x, y, and z. The projection of the 3D object is going to get projected onto a 2D surface, resulting in a loss of a dimension. And the loss of the dimension being depth. Right? All we know is that the projection is going to be a certain distance behind the lens. We do not know how far the object is in front of the lens. The loss of dimensionality is what we call perspective projection. Okay? Now, of course, there is a relationship between the 3D object, its size, geometry, to the 2D projection. Right? And we'll try to understand what this relationship is, but we'll define for that first a coordinate system. Okay? So for the real world coordinate systems, the 3D space, we'll refer to everything in that space with capital X, Y, and Z for the 3 dimensions. The origin of that space will be at some arbitrary 0, origin, okay, 0, 0, 0. And in terms of defining our optical geometry, we'll define that origin to be at the center of the lens. Okay? Now, for the image that gets projected from that object, we'll define an image coordinate system, and we'll refer to that with smaller letters, small x and y denoting the 2-dimensional coordinate system or the projection. Okay? And we'll assume that the plane on which the image is projected is parallel to the 3D plane, right? So in general, that plane would be perpendicular to the z-axis. Okay? We'll also say that the optic axis of both the coordinate system pass through the lens center. Okay? So the origins are all in line. All right, very good. So if I convert that simple drawing into our planar projection system, what we have is some plane in the 3D space, right? The plane on which there is an object, and the plane is parallel to the xy coordinate system. It's going to project back onto our image plane, the plane being parallel to the world xy coordinate system. And, of course, the origin of the 3D coordinate system being the center of the lens. Okay? Now, if we assume that the center of the lens is just a small hole, right, we can think of this as what we call a pinhole projection system. Okay? Now, there are subtle differences between pinhole projection systems and lens projection systems. A lens projection system, by definition, allows for a lot more rays of light to pass through it than just the one in the center. Okay? A pinhole system is the one that will reject every ray of light except for the one that passes through its center. Okay? So we'll make that assumption for now. So that's the easiest way of defining how these geometries relate. Okay? Now, of course, rather than actually having a focal length that's behind my lens, if I simply take it in front of the lens by the same distance f, I would end up with what is called an upright projection system. Right? The geometries don't change. All I now have is a projection plane that is the same distance in front of the lens. Okay? This assumes that you have a lens which is perfectly symmetric. Okay? So we can look at this geometry. It's much easier to relate to because now you have projections that are upright. Right? Things are not inverted. First, that, and second, I don't want to work in negative coordinate spaces. Right? All right, so let's look at a single point in the 3D space. Right? We'll call that at some point A, comma B, comma C. Okay? That point is going to project onto our imaging plane at a point small a comma b. Okay? Of course, this plane, remember, is a certain distance f in front of the lens. Okay. Now, this diagram should show all the coordinates that we have for the simple projection model. Okay. Now, how do we relate? What is the relationship between this A comma B and the point that exists in the 3D space, A, B, and C? Okay. So to do that, one way to define that is simply by looking at simple trigonometry, or in this case, we'll look at equal triangles, right? The laws of similar triangles. So the laws of similar triangles tell us what? That if I have triangles, right, two different sizes, as long as all the angles, the respective angles, are the same, then the two triangles relate to each other based on their proportional lengths, relative lengths. Okay? So if I define each side of the triangle, in this case by EF and D and small EF and D, then D by E will relate to D by E of the smaller triangle, and so on. Okay? So the relative lengths should remain the same. That's the law of similar triangles. And we can apply the same thing in order to understand our projection geometry. Right? So we'll simply break up our projection diagram into similar triangles. Right? In this case, I'll define triangles by the point in the 3D space at the distance c from the lens, right, in depth, and of course at height b in the xyz, and the projection of it at distance f from the lens and at a height small b. And similarly, you can define the other triangles. Okay. Now once I have the triangles, I can start relating their relative lengths. So A divided by small f is equal to capital A by C, and B divided by small f is equal to capital B by capital C. Right? So this tells me a very simple relationship that every point in the 3D world with coordinates A, B, and C will project onto my 2D plane, whose coordinates will be given by A divided by C and B divided by C, each one multiplied by a factor f, right, which is the focal length of my lens. Okay. Now f divided by c, you can think of it as a constant scale parameter that will scale every point in the 3D space to find its corresponding projection in the 2D plane. Okay. You can generalize this to f divided by z, z being the distance of an object in the 3D space from the lens. This f divided by z will be a constant scale factor. We typically refer to it as the magnification ratio. Okay. It's a magnification ratio that basically scales objects in the 3D world onto the 2D plane, imaging plane. It's a very simple relationship between 3D objects and their 2D projections. So, right, very simple examples, we can understand the relationships. If you have a man that's standing 10 meters out, okay, and is 2 meters tall, if I have a focal length, for my eye, generally it's about 17 millimeters. Question is, what will be the projection onto the retina? Right? And the answer is relatively simple. You essentially will have a projection which is 3.4 millimeters on the retina. Okay. So this simple geometry gives us a very simple relationship. Keep in mind that this is a simplified geometry based on the assumption of a pinhole projection system. Right? Think of it as a lensless projection system. The minute you have a lens, normally we do not have what we call a perspective projection system. We typically have what we call a weak perspective. Right? The assumption of perspective only holds true for perfect pinhole systems. You put a lens in, you are allowing a lot more bending of light. It's not only through the center that the light is going through, so we have a pinhole violation, a weak perspective comes into play. Okay? A weak perspective, we'll come back and look at it a little later. Okay? All right, any questions on any of this so far? Yes, I know. This time I'm looking at the time. We will stop here, but I just want to know if you have any questions on anything we talked about today. All right, very good. In that case, I'll see you on Thursday.